have this bar, length L, mass M. I'm going to mount it so that it pivots about this point, a quarter of the way in from one side. And I'm going to hold it horizontally and let it go. So question A is when just right after I let it go, the instant I let it go, what is the instantaneous angular acceleration of the rod? Again, there's a pivot point right here. So like the instantaneous acceleration of the rod, the angular acceleration. Of course, if I let it go and watch it for a moment, it will swing downwards. All right? To something like that. Pivot point still here. It's now spinning about that pivot point. So question B, I'd like to know the velocity of the bottom. How fast is the bottom of the meter stick traveling? V, the linear speed of the bottom of the meter stick. It's not a meter stick, but I'm using that as an example. But here's a question I didn't ask yesterday. Don't care, because I asked it first semester, and so you should be good at it. How much force is the pivot having to provide to keep it from falling? What's the upward force from the pivot point right when it's perfectly vertical? And again, I'll make it very clear. None of these are new questions. I've asked every one of these questions before, and in some cases, I asked them. I think most of you probably understand what my hints are. I mean, maybe not, but I'm hoping some of you do. But there's something massively bad out there. What's the moment of inertia? What are you using for the moment of inertia? I would be careful. I gave you a whole table of them, and this isn't on there. I think you'd have to use parallel axis theorem. This is not a bar about its end. This is not a bar about its middle. It's certainly not a ring, a ball, or a disc. So when I made a whole big play for 4 days about the importance of inertia, that must have sailed right over the top. See what I mean? Disappointment. All right, class. Disappointment or not, I don't know how long I want to flounder on this. We have more things to be sad about. So let's... Also, this is in your homework. So you should be trying your homework. This kind of stuff's in there. We'll need the moment of inertia before we do anything else. I will use the parallel axis theorem to find it. I do know the moment of inertia of a bar about its center of mass, but I do need to shift that now to a different location from the center of mass to 1/4 of the length of the bar away. So that's going to mean 1/12 ml squared. That is the moment of inertia about the center of mass. And I am shifting it a distance of L/4 away from the center. I'm assuming you know why. That you can understand that from the middle to 1/4 of the way from the edge is 1/4 of the way from the middle. I'm not convinced you know that. And in fact, there's probably people right now who don't know why I used L/4. But most of them won't ask me about that for another 30 seconds, so that I'll be frustrated when they do. But this will be 1/12 plus 1/16, which I know is going to be 7/48, I think, when you get common denominators, which you will have to do between 12 and 16, ml squared, which makes the moment of inertia of this system kind of a mess. But this is what it is. So, since that's used for every portion of our calculation for A and B, now we have something we can base it on. Yes, Victoria?
why is it not, like, why didn't you use the one that
Am I rotating about the end of the rod?
oh, okay.
Okay. Are you sure?
Yeah.
We could break it up into two rods, both spun about their end, one rod 3/4 of a length long and one rod 1/4 of the length long, if you want to use the end one, but I just don't think that that's any more advantageous. It gets you 7/48. You sure? Awesome. Well, now we have the moment of inertia. I say we do part A. Part A, I have the rod just horizontal. That's it. I don't have to worry about anything else. I am instantaneously looking at the torque on the rod the moment it's released. By the way, there are two forces acting on the rod the moment it's released. If the pivot point is here, there's an upward force on the pivot point, equal to mg actually, because net force is 0. But there's also a downward force acting on the center of mass that's equal to mg. Remember, when we're dealing with an object that's got extension, we assume that forces act at the center of mass. That's why we call it the center of gravity. So there's a force downwards at the center of mass. This becomes the torque arm length, the distance from the pivot point to the application of the force, which is a distance of L/4. So if I want to calculate the torque from the weight, remember R times F times the sine of the angle. R is going to be L/4. F is going to be mg. And it's going to be the sine of 90 degrees because at the instant it's released, gravity is perpendicular to the torque arm. Nothing weird there. Yeah, I saw your struggles, but there's nothing weird there. What does that have to equal? It has to equal I alpha. It's an unbalanced torque. The force on the pivot point does not provide a torque because it acts at the pivot point, so its torque arm distance is 0. So although there are two forces acting on the bar, only one of them causes an acceleration. I'm not saying that for my health, by the way. I'm saying that because you should be aware there's more than one force acting on the bar and know why some of them cause torques and some of them don't. It's going to come up. So 7/48 ml squared alpha. And this is, let's see, LMG/4. Now, apart from all that, this is just algebra. It's a mess of letters and numbers of which you're going to have to kind of work on it. I want alpha by itself, so if you need it, that'll be 48/7 ml squared times LMG/4. I tried to skip through these steps in 6th period. That was ineffective. So I'll cancel a 4 into 48. That's going to give me 16, right? Should probably check my arithmetic. And I'm sorry, what is it supposed to be?
12.
Thank you. Just making sure. I even said to check my arithmetic, didn't I? Cancel out one of these L's. Cancel out the M. And it looks like alpha is going to be equal to 12G/7L. Now, how do you have any idea whether that's the right answer or not? Well, I have some idea. G is in meters per second squared, and I'm dividing all that by L, which is probably in meters. That's going to give me units of radians per second squared, and I'm looking for an acceleration. I have high confidence that my algebra is correct because my units seem to work out in a plausible way. These are the kinds of things you can do to help check, but do you know if it's right or not? 12/7? It's not like it's anything special there. All right, that was question A. Shall we move on to question B? Looking at question B, the first thing I'm kind of thinking about with question A is that at the start, the center of mass is going to swing downwards to a position right below where the pivot point is. I'm looking at just the motion of the center of mass, because the amount of potential energy is based on the change in height of the center of mass. And that's going to be equal to the amount of rotational kinetic energy of the system if nothing takes any energy out of the system. What is the change in height of the center of mass? If I make this the reference level, this height is L over 4. So how much energy does the system have? mg times L over 4. It's the amount of gravitational potential energy. All I'm looking at is the change in height of the center of mass. Now, when the actual bar does twist downwards and is right about there, and it's moving, well, it's going to have a rotational speed given to it by the fact that it accelerated the whole time due to gravity, but that rotational speed is going to have to be related to the amount of energy in the system, 1/2 I omega squared. This is not the answer we're looking for. This will give you the rotational speed at the bottom. Although you were asked for the linear speed, this will only give you the rotational speed. You might have to do this as an intermediate step, just like yesterday. Now, it's still a mess. This is not pretty. This is mgl over 4, and that's going to equal 1/2 of 7/48 ml squared times omega squared. Nothing pretty about this. It's just letters and numbers. They obey a set of rules. Follow the rules. I'll get 96 over 7 ml squared times mgl over 4. That equals omega squared. I'm trying to get omega by itself. Just doing algebra. 4 and 96, I can cancel and leave 24 up there. M's go away. Yay, bye-bye M's. And L goes away, just like before. Yay. And I see 24g over 7L. And that equals omega squared, so that all equals omega. Again, do I have any idea if that's the right answer? Well, I can check the units. I've got meters per second squared in the top and meters in the denominator, so it's per second squared. And I take the square root. That sounds like radians per second to me. But wait, there's more. We want how fast is the bottom of the meter stick going. Careful. I've seen this mistake made already. The bottom of the meter stick is a distance 3/4 L away from the pivot. Well, some people understand the implication of that. Some people don't. But in this case, R is going to have to be 3/4 L. Yep.
So the center of mass doesn't matter, it's just the distance from the rotation?
Well, it mattered in determining how much energy there was, but not in this case. It doesn't determine how fast the end of the rod. I mean, it does, because it determined how fast the whole rod would be traveling. But this particular speed, the length we have to use to calculate it, will depend on where on the rod we're interested. Now, if we were interested in the speed of the center of mass, I'd put 1/4 L in there. There's nothing special or nice about this, except that some of it's under the radical and some of it's not. You could clean this up by canceling out some L's, by putting them under the radical and stuff like that, and you should. But I'm not doing algebra. We have too much I'd like to talk about besides this, and we're not quite done yet. So, moving on to question C. I'm gonna kind of leave omega. Well, omega's right there, so I've got omega. We're gonna need omega. Because for question C, I have a bar which is pivoting about this point right here. The center of mass is there, and the whole thing has a speed omega. And I want to know with what force is the pivot pulling upwards on the bar. Now, this one we haven't talked about. You could be forgiven for not knowing all of the things you would have to do. Okay? Forgiven is a weak relief, though. There's two forces acting on the object, and they act along this line, with the force on the pivot upwards and the weight downwards at this moment. So the net torque on the system is 0 at this moment. However, the system is accelerating. There is a centripetal acceleration in this direction on the bar because the center of mass of the bar is traveling in a circle. So the net force on the center of mass has to conform to MAC. I'm trying to say my words very carefully because in a moment, after I write in, well, I didn't say T. After I write in that F upwards minus mg is the net force, I then have to write that this is equal to m omega squared times r, right? Centripetal acceleration. Anything weird here? We've done this before, first semester. The only thing that's weird is what do you put in for r here? And I'll be very clear. This is acting on the center of mass. It's causing the center of mass to travel in a circular path. So this is going to be L over 4, the distance from the pivot point to the center of mass. That's important. That's worth writing down. Also, whenever you do a problem like this, it is very likely that your force is going to be proportional to the weight of the object. It is weight that caused the object to swing downwards in the first place. So you'll generally find that your answer is going to be a multiple of the weight, and we're not going to be disappointed here. Omega is 24g over 7L. It was square rooted, but I have a square here, so I get rid of the radical. And that's all times L over 4. Now, I'll do a little algebra here. 4 and 24 gives me 6, but the L's cancel, which I find to be interesting, that the length of the bar doesn't actually matter. Just where I've pivoted it matters. When I do that, you'll notice I get 6/7 mg. Like I said, most of the time on a problem like this, you can tell you've done it right if the force is some multiple of the weight. And in this case, it is some multiple of the weight. I hate to do this, but I would not normally have written this out, but this came up. You can combine these two things. Do you know that? Not everybody in the room does. But mg plus 6/7 mg can be added together because they are both mg. Getting common denominators, you'll get 13/7 mg. Yeehaw. Now, I'm sorry. I'm a little disappointed by how illuminating this all is to you, but all of this is something we've already done. All of it. The only thing we had not done before was have to come up with our moment of inertia at the start. But everything else has been described in this room. But I'll be honest, this stuff is tough. There's a lot to bring together here. Would you agree? Tiny little things. You have the entire equation sheet and all of your notes. Boy, there's a lot to keep track of, isn't there? But you saw it, right? I'm not making these problems up. This is what we have to do. And having gone through it, whether you want to believe me or not, It's all just application of net force or conservation of energy. There's going to be a reason why you use one versus the other. Well, I would bat this around longer, but there's more learning to be done. So I want to talk about another example. And yes, I'm going to say the words you hate to hear. You've done this before too. So I have a ramp, H high, box, and let's say for this example that there's no friction on the ramp. Release the box from rest. How fast is it going when it gets down here? With the information I've given you, there's only one way to do this problem. And you should be almost done with it. It's super simple, super fast, and we've done it so many times, you should have it memorized. We just used this principle too, so don't feel so bad. Square root of 2gh though, right? There's not much here. What kind of energy does it have at the top of the ramp? What kind of energy does it have at the bottom of the ramp? That's it. mgh here, 1/2 mv squared at the bottom. If nothing takes energy out of the system, these two amounts have to be equal. You can't use forces because you don't have the angle of the ramp. And I didn't give you enough information to find the angle of the ramp. You had to use energy. I forced your hand. So the velocity at the bottom, just set these two equal to each other. And I'm writing this out not because I want to, but because I know there's some people in the room who need to see it. M's cancel out, solve for V, and the velocity equals square root of 2gh. Now, this isn't what I really want to discuss. I want to use this to get us started. And like I said, if you couldn't do that, you understand how disappointing that is, right? So let's get rid of the boxes. They are in the way with what's going to happen next. And replace them with something that has a different shape. Maybe where the shape will matter. A disc, perhaps, or a ball. Who knows? There we go. If I release it at the top, do you think it'll be traveling faster or slower when it reaches the bottom? Faster, all right. Anybody vote for slower? Anybody vote for what's left? The same? So who votes same? Who votes faster? Who votes slower? Wow. Intuition serving you guys terribly. Right now it's the same. Is there any reason why this thing would roll? There's no friction. That's right. As long as there's no friction, there's no reason it would roll. And since the mass cancels out, the shape won't change the result here. This is referred to sliding. And although these words might not sound like much because they're obvious and you know what their definitions are, in physics they might have specific definitions when used in a problem. An object that's sliding isn't rolling. Its rotational speed and its linear speed are unconnected. And in the case of this problem, this specific example, because the coefficient of friction is 0, means that there will be no change in the angular speed. There can't be. There's nothing to provide a torque that would change the angular speed. Objects that have the potential to roll, something that's round, the only way the angular speed changes is if there's a frictional torque or a point about the edge that friction could use to cause a torque. There's nothing here that can cause a change in the rotational speed. So under this circumstance, it might have some amount of rotational kinetic energy, but whatever amount of rotational kinetic energy it has, it will still have that energy at the bottom. So only the potential energy can be converted into its linear kinetic energy. Now, that's one possibility. Another possibility is something called slipping. Slipping could be construed as a situation in which there might be a certain amount of friction. And that means that there can be a change. I'll put a little check mark in there, that there might be a change. I don't want to say whether it's constant or not. I don't know. That'll be situational. But under this circumstance, a frictional force could cause a change in the angular speed. But with slipping, without more information than that, I don't know how much of the rotational kinetic energy will influence a change in the translational kinetic energy. Meaning, I don't know if the fact that it's slipping is going to make it go faster or slower, or stay the same, or what. All of that will depend on how much friction there is, what direction the object's already spinning. Or maybe I start it from rest, and as it slips down the ramp, it might start to be rotating, but it doesn't rotate fast enough for the next condition, which is rolling. Rolling is a specific condition. If the word rolling is used in the problem, then they are specifically stating that the angular speed and the linear speed are locked together. If you see the word rolling, they are stating something. There are plenty of problems that have sliding and slipping, but there are very few problems that commit without saying the word rolling to be somewhere in the middle. If they say it's rolling, they are stating something specific. They are giving you information. We're going to focus for a while on problems where rolling is occurring, where an object rolls down a ramp. In all of those problems, be paying attention. There must be a coefficient of static friction sufficient to allow rolling. It has to be static friction because the point in contact with the surface isn't sliding. The point that's in contact with the surface is at rest with respect to the surface. More importantly, in a situation in which an object is rolling, when we reach a point in the problem where we want to deal with its energy, it will have both kinetic energy for translational motion and kinetic energy for rotational motion. And they're linked together by this. How much they turn is related directly to how fast they're going. Now, if an object rolls down a ramp, do you think it'll be traveling faster or slower than an object that slides down the ramp without friction?
Slower.
Why?
Because instead of all the kinetic energy being translational, there's rotational kinetic energy as well.
Perfect descriptive answer, and what I would hope all of you would say. Objects that roll tend to be slower than objects that slide without friction. Not tend to be, have to be. because the energy is now being divided amongst two different places. We have the same amount of energy, but now some of that energy has to be used to cause it to roll. By the way, it's more than just that. An object that is rolling is experiencing a frictional force. So even though it's got a mg sine theta down the ramp, none of the net force stuff changes. So I have mg sine theta down the ramp. There is still friction up the ramp in this circumstance where it's rolling down the ramp. That's going to cause less acceleration than an object that slides without friction. So, let me just rub your nose in it a little bit. This is what the part where the teacher gets that moment where they can say either, wow, see, we did this, why can't you? Or you guys retort back, well, Mr. Shelton, if you'd been a better teacher, perhaps we would remember how to do all this. But what if I had a weight M on a string length L and I released it so that it swung downwards? I could ask all those same questions. It's the same freaking group of problems, right? And we've done these. And it might be like, what is the tension in the string at the very bottom? Sound familiar? It should. We've done this problem before. If it doesn't sound familiar, then the door's right there. You should probably just go home now. But this should sound familiar because we've done this. Again, I know that you don't remember anything from last week, last month, last year. But you're going to have to if you want to pass. Gloves are off this semester. Got a lot of A's in the room. I'm sure you all remember this stuff from last semester. You earned those A's, right?